Good afternoon. I'm Bill Nair of of PDF Solutions. I'd like to thank Dongbu, Lou Hutter, and Dr. Park for inviting us here today to give this overview on analog yield optimization. Our company is a little bit small. We are an engineering consulting firm that specializes in yield ramp-up technologies. And we do consulting projects with many companies around the world, many of the foundries that you heard of today, and as well as the IDMs. But today, since this is the analog forum, I would like to specialize and just speak about some key strategies, or at least what I think should be the key strategy for analog yield optimization. Oh, I think I went too fast. Okay, so the outline of what I'd like to speak about. First, we'll discuss a little bit of what I think the key factors for the analog IC technology are. Then go into the methods to characterize variation, methods to optimize the circuit performance, and finally, fault detection and control for variations. What I tried to do is organize this so that we have one key example for each one of the areas. That would be PDK and design technology, as well as factory control. If we just take a look at one foundry's portfolio, or one analog manufacturer's portfolio of parts, you can see a wide diversity of parts shown here in the in the product function, all the way from audio amps that have very small 2.5 or small percentage of logic area, and therefore high analog area. RF barcode reader, on the other hand, is 87% logic area and only 13% analog. This presents somewhat of a problem. How do you optimize yield for this variety of parts? You can see total chip areas are quite diverse as well. So there's really no one key strategy for all, but if I had to pick an overlying strategy, we would break it down like this. The problem statement: analog products are uniquely designed to fit the application. And so as we saw, the analog-digital partition is quite diverse. I think that even though we saw earlier the chip stacking and the dual package, or dual chip in the package, single chip solutions are still thought to be the best for low power and end user package space. Analog components interface to the real-world sensors. So we also saw today a variety of high voltage transistors, all the way from, let's say, 10 volts up to 1,000 volts or higher. We know that there's precision capacitance and resistance that are needed in some of these components, as well as precision transistors to minimize things like offset voltage. It's quite diverse. And third, we know that the advanced node CMOS is creeping in. As we saw in Dr. Hu's last presentation, we saw that the advanced node CMOSs are starting to come in and enable, let's say, digital signal processing to replace some of the analog circuitry. So the analog-digital partition is changing on a lot of our products. One thing that I found through my experiences is that sometimes, you think you can work the mixed signal solution or the mixed signal analog solution on an older technology, but actually, even though the digital part might be small, the interface to the high performance or high speed system sometimes needs to be reconciled. So you need to work on advanced node CMOS to solve some of those problems. And then finally, we find ourselves with memory components are sometimes needed for trim calibration, and those are added in and add complexity. All of this results in a couple of constraints or key points, is that no analog yield penalty is allowed. I think that everyone expects from the product development side not to have any reduction in yield or therefore higher cost just because we have some analog function, especially in the case of high digital partition. And then also the advanced CMOS costs more to make, which makes the analog real estate, so to speak, very expensive. So if you have large blocks of analog that can't be shrunk, this becomes very expensive as you go into the more advanced nodes, taking advantage of those capabilities. So what is one of the main strategies to take care of it, of the analog problem? High tolerance specifications and accurate models. So we have to have high performance systems, and that requires a very tight tolerance on these components that are added in to make to enable the analog functions. Oh, sorry. And what that does is that gives you a cost advantage from the reduced die area that the resulting design consumes. It makes it extremely, it also requires an extremely efficient characterization in the technology development phase. You'll find, especially in the case as the lithography node shrinks down, that layout attribute now create device dependencies, or devices are dependent on certain layout attributes, proximity to a poly, proximity to active area, and so forth. And then you find that there are systematic process and lithographic issues with flow integration. So you have advanced node CMOS processes that have very shallow junctions and very tight thermal budgets, and now you're integrating some of these analog components. These all have to be characterized very early on and minimized or eliminated. The second strategy, or the second point in the strategy, is you need to have reliable production. So if you take the route of providing your product development group with a very high performance process, tight windows, well characterized, you need to, you should get a cost advantage also from the higher yields. And this requires increasing tool level knowledge, tool matching, and monitoring all within the foundry or the fabrication facility. Because if you implement that high performance specification, you must maintain that specification through the lifetime of the product. Otherwise, it's not worth it. And finally, we need to minimize any shifts to those components due to stresses in the field. This is a reliability area. And what you get out of that is, of course, customer satisfaction from the highly reliable products. And a lot of times, I've found in my experience that analog components and additions to digital processes sometimes have created these reliability, weak points. And you also, to support that, you need to maintain processability and conformance to the original qualification process distributions. Sometimes we find in analog products that not every performance or every feature can be tested at the wafer probe or in the final package test at voltage and temperature. Sometimes application brings out the real issues. And so what we find there is that even if you're within spec in the factory, if you're off distribution from the original qualification, you may get some surprises. So the strategy becomes, in my mind, is characterization of the device variation and knowing the sources of that device variation very thoroughly. And then because nobody can carry all the burden in the product development side or the layout side, we need to find ways to minimize variation through layout. I think that was a point that's going to become increasingly important as mentioned in the earlier keynote speech. as the Moore's law starts to get compressed or it ends up, what is going to differentiate your design or your factory from other factories that are producing. And if you can do various techniques to minimize the variation through layout, kind of a DFM, that will be one of the differentiating points for your firm. And then finally, minimize the variation in fabrication, fab line. That's pretty obvious. So the sources of variation, we have developed techniques and infrastructure that I'd like to explain to you of how to characterize this variation so that you can properly define your actions to minimize it. You can see here on the left side that we have minimum device width and 1 micron device width, relatively large. And we can extract information from our test structures to look at the within die, die to die, wafer to wafer, and lot to lot variations. And we find these things to be very consistent on a given process node. And you can see the variation also from the layout effects. On the right side, in the red, you have the loose pitch transistors. And in the blue, you can see the tight pitch, same transistors that are drawn with a tight pitch, and you can see that just the general distribution is wider, or you can see an opportunity to create, let's say, a smart PDK that can differentiate between these two types. So we can go through and classify the sources of variation into systematic and random. We spoke a little bit about the layout and neighborhood in the systematic side, but there's also systematic process variations across the wafer that are induced by the particular equipments that are used, or the particular recipes or particular settings of those equipments within the recipe. The random variations are distributed between intra-die and inter-die. And the ones that are particularly important to us are short-range mismatch in many analog designs. We think that the devices of identical layout and neighborhood, we have these sources of variations, random dopant fluctuations, across-chip variation, and so forth. And systematically, we have process gradients that I had mentioned. So we feel that the best way to get a very good handle on this is to have a very complete infrastructure that includes the test patterns to take care of the characterization, as well as the software and the test equipment necessary or at high enough speeds and high enough capacity to capture all the information that's necessary. And those result in the improvement plans that can be created, through engineering projects, design enablement, and DFM strategies. So in the areas of test structures, it's quite routine to have test structures between the product die on the wafers. But we've developed highly multiplexed arrays and pad-efficient designs for these test structures so that we can get a multiplicative factor of, let's say, between 5 and 10 times the number of devices that you would normally get in a, let's say, we call it a scribe line monitor. And these become very important to collect the statistically significant information. And we also have strategies of placing the array below the pads for more efficiency. The experiments that we implement on those test structures are shown here in just example case A, B, and C of various environments and features that are in proximity. And you can see that the confidence, the detectability with the confidence level on the right side kind of saturates out with the number of replicates, but you actually do need and you can determine the number of replicates that are necessary to gather the information. And these are all important to determine accurately the information that will go into our models. To get broad coverage across the wafer so that we can do an accurate wafer map of the across wafer information, which has to do with the nominal value variation, which is important to the spec window. We've developed strategies of putting scribe lines across the stepper field that are schematically shown here. And then this becomes a problem in test time, but we have that some strategies there as well. We heard earlier about leakage. Device leakage, of course, is a tremendous problem as the advanced technology nodes are pushing the physics of the transistor, as well as in the analog space. So we've developed leakage arrays that can characterize all the sources of leakage and break down by let's say, by feature or by physics. So you have the drain to source leakage, the poly to poly leakage, gate to source leakage that are sometimes hard to deconvolve from the normal production e-test data. So in order to gather all this information, it's very necessary to do it in real time and not burden the manufacturing, because one of the points that we heard in the talk just before was about turnaround time. So we can't spend an inordinate amount of time to collect this information. So the solution to this is to develop a system specifically for characterizing our structures. Our terminology, we call it a PD fast test 2 or 3, that's shown here. We have 72 analog test channels, and this system design results in about a 60 times improvement in test speed over a conventional tester. And with this information, we can gather information again about the layout attributes. You can see the gate pitch, and as well as some of the lithographic issues that show up. Here I've shown some gate corner rounding that's dependent on the space. All of this information needs to be incorporated into your models. Typical 65 nanometer process that we've done quite a few projects on, greater than 10. We find these type of variations by the corresponding layout effect shown on the left side. You can see things that are in the area of 1 to 10%, 6 to 10%, 12 to 18% in iDrive, just due to the SDI stress and the process features there. So if you, let's say, just add these up in a statistical way, you can see that there's quite a bit of variation. And what does that mean to us? That ends up in broader distributions that are then transmitted into the PDK. So what we suggest to do, and I think there's quite a bit of work in this already, in many fields, but we have developed design tools for transistor level design, Monte Carlo simulation, design of experiments, response surface methodology, which maps out the variations across the different parameters, and feed those into the SPICE models. In addition, you can see a lot of times the SPICE model will give you a slow and fast corner. Those are shown here with the X. And you can see the distribution of the process is maybe only using about 50% of the area that's covered by the slow and fast corners. And even the 4.5 sigma corners are quite broad around the actual distribution. So software that we're using takes the e-test measurements, which are shown in red, and we can do a Monte Carlo simulation, or Monte Carlo based simulation, to do our SPICE models. if you have that capability, it then becomes quite natural, I think, to combine that to your particular circuit layout and your circuit design. So the key technology here on this slide is what we call a circuit surfer, which is a parametric yield modeling. So I think most people that are involved in the analog yield and analog processing and analog design know that a lot of the yield can be lost. If your yield is very good as far as random defectivity is concerned, because your fab is clean, your equipment processes are clean, you can lose a lot of yield just in parametrics. One resistor value showing out of spec, or one transistor being out of spec. So what we've done is keyed on that and spent a parametric yield modeling effort. A result was one of the PDF's first products, the Circuit Surfer. And some of the output is a process design sensitivity matrix, and we can go down and output the optimized design parameters and simulated optimized functional block outputs based on the statistics that we've measured. These are key points in your design. The results are that you can achieve the best case die area. And so if you have a die that's, of course, 10 or 15% smaller than it would have normally been by going through a normal design practice, that's just another way of increasing the yield. Through these characterizations, we found one thing, and I think this is also known, that local variation does not scale as we go down into the advanced nodes. There's a lack of TOX gate oxide scaling that's evident like around the 90 nanometer node. And you can see as you go up, as you go down in the Moore's Law curve here, 65 nanometer, 45 nanometer, actually your distribution, your spread of the VT in the local mismatch area becomes increased. This is due to a number of effects. There's a very shallow junction process, very short time thermal effects, and they all lead to dopant fluctuations, and even some of the advanced lithography that's used for these nodes actually works against you in some of the delta VTH. This is especially true, or this was first very important in the logic side for the SRAM block V-min characterizations. But we also know that this is an important effect for the analog designer, who especially is working in areas of matching devices, which would be matching transistors or matching capacitors in the case of switch capacitor filter design. So if we have a really good characterization, we have a statistical based PDK, it's quite natural to think that we can do a stochastic analog or RF design. Now, typically, what's been done in the last 20 or 25 years on this design is certain techniques, like dummy devices. You can see here, if you want to match transistor M1 and M2, it's well known that transistors on the end of transistor arrays behave quite different than transistors that are in the middle of the pitch. In fact, that was seen in the layout attributes in the slide earlier. So one easy way was just to put dummy gates in. Of course, what does that do? That increases your effective area just to achieve the matching spec. Other techniques are to use common centroid concentric layout side approaches, where you take half the gate, the other half of the gate, and match these two against these two, and so forth. But these are also, if you look at the layout, quite area consuming with the extra contacts and so forth. In the end, there's one model that if you have to do the offset voltage minimization, you can use multiple transistor fingers to create enough W to average out the variations. That's a very common technique that's been used for quite a while now. But it can't be used too much in the future if we're continuing down the advanced CMOS node. There's diminishing returns using the larger devices to average out the fluctuations. You can see that here from the Pelgram model, which shows the sigma of the VT inversely proportional to the area. And as the area starts increasing, it's just a simple equation here, you start increasing, you cannot get down to a mismatch level that may be required by your 24-bit ADC or some high-performance product. And in fact, if you look at it, if the analog area stays the same or even grows, and if you're moving from 130 to 110 to 90 to 65 digital to try and get that Moore's law die size shrink, which is important, and your analog blocks don't shrink, then that's where your real estate becomes a little expensive. So this model is basically, in the end, it's as the it's inversely proportional to the square root of the area. One of the technologies that we've been involved in through our academic or our ties with Carnegie Mellon University is we are working on fabrics of transistors. And those fabrics of the reason we use the word fabric is in a logic design you see a wide variety of transistors with odd layouts, and these are all generated by the layout system. We try to organize those into a uniform fabric. It's something that the technologists learned from the SRAM design and minimizing variation between the SRAM transistors. And in the course of using those fabrics, it was something that then became obvious that went back to the analog designers is match pairs can be improved, or the matching can be, the matching can be improved by just increasing the number of units to average out the mismatch. But since you're now using the advanced node CMOS, you can actually do some smart selection of particular transistors to form the minimum mismatch. And so the data is simulated and actually reproduced that if you can use this computational method to select out pairs and take a look at what point do you have the mismatch, we find that about half of all subcomponents are used. Half of all these transistors, selected properly, can be used to find a minimum mismatch. And so you can go from like a non-optimized configuration of 11.8 or 12 millivolts down to something on the order of a quarter of a millivolt just through these smarter techniques and these regular layout arrays. There is some circuit overhead there is some circuit overhead in this technique because you are doing some computation and you're doing some storage and memorizing which transistor pairs to use. But it might be the only way to meet specs and reap the benefits of the next generation technology and make higher performance, let's say, ADC. So you can see here, this is one chip that's been, or one experiment that's been implemented in silicon. And you go from the Pelgram model, which is 1 over the square root area that we looked at in the previous slide, you go to something that's now just dependent on area. You've removed that square root aspect. And so if you are spending 5 or 10 times the area, you can start to now see wider and wider benefits that you didn't previously see. So this is one way that when we're trying to reduce variation, that the product development side of the aspect can let's say, share some of the load. Of course, the fabrication has to share some of its load as well. Some of the other areas that we're working in right now are in the area of what's called fault detection and control. I'm going to go through kind of quickly on this fault detection and control, but I think we can get the idea. what you have here is you have wafers going into a fabrication line. You have various process modules, isolation, gate, silicide contact, metals, and then you have die sort yield at the end. So each one of these wafers, of course, runs through operations that we call processes. And each one of those processes have equipment. Each one of those equipments have sub-recipes. Each one of those recipes have temperature, pressure, RF power, various readings that go in to make up that process. Now that we have the computational power necessary to gather the data and analyze it, it seems to become natural just to take this data and see which one of these equipments or processes relate to the die sort yield. And then just put some limits on it. But actually that becomes very difficult to do. And if you take a look at just one module, which would be the Metal 1 to VO1 module, you can generate what we call indicators. You can generate 200,000 indicators totally. And if you run 10,000 wafers a month, you have to make about 3 million observations per hour to characterize all the equipment functions. And if you put a control limit of about 5 sigma, that means you're going to generate about 2 alarms per hour. And of course, that becomes unsupportable because some of those alarms are generated by equipment functions that went out of spec, but actually are not meaningful to yield. So then it becomes wasted energy for you. So at this point in time, there's no way to systematically prioritize these FTC monitors down to a critical few based on the product yield and therefore the cost impact. And also, we found that there's FTC and, let's say, yield management system software tools and databases that were not really matched up at this time. So what's being developed at this point, and this by our firm, is what's called a yield-aware FTC modeling. And the purpose of this modeling is to take knowledge from tools, knowledge from processes, knowledge from the product yield impacts, but actually send the indicators that are generated. Here's the 100,000 indicators, or let's say, as we showed earlier, 200,000 indicators. Send those through a modeling environment that's being developed, and remove just the principal components. We can get down to about 10 to 2,000 variables. And if we continue the modeling into a second stage, and it's just too detailed to discuss at this point, but we can get the defect density of the via failure rate down to about anywhere in the area of 3 to 15 indicators. Usually it's more 3 to 5 side. At that point, we've got a model that relates to the, let's say in this case, the via failure rate, but it's really also applicable to any of the parametric functions that control analog yield. We go through a loop that involves the model validation, and we do prediction, recalibration, rebuild, looped in with the root cause drill down. Root cause is very important because we need, once you make a statistical-based model, you like to understand what the root cause is so that you can be assured that it's real. In the end, what we've created is various parameters, in this case via failure rate, or it could be threshold voltage or sheet resistance of the N+, as a function of a reduced set of key indicators. And those become then very valuable in the factory maintaining control on variation, because now you actually can take action on those key parameters if they're the ones that impact yield. I brought a couple of examples. I hope it's easy to visualize. In this case, this is one of the, these are all actual works that we've done in our projects. This is a parametric model. It involved a variation of threshold voltage from low to high across the wafer. And you can see we've taken data, using our automated testing system that we've seen earlier. And we noticed that there's a large within wafer PMOS VT variation that was causing yield issues, actually. From the YFDC modeling, we identified the key yield parameter. And it was found that the threshold variation was caused by stabilization temperature and not the spike in yield as expected. Those of you that are in the room here that are in the process technology side will recognize that this is a rapid thermal profile of the temperature versus the process time. And in going through the root cause analysis, or let's say in trying to understand what was the problem before modeling, it's always thought that the peak temperature, which is the temperature that's used to activate the dopants in the silicon, would be the source of the variation, because this is maybe typically 400 degrees and this might be over 1,000 degrees. And so this one is always thought to have the higher impact. But as we went through the modeling process, statistically this didn't show to have any effect, but variations in this temperature stabilization area were had quite an impact on the wafer variation. And then out of that, actually the fabrication facility could go through the equipment. Now that he knows what equipment it was, what key indicator it was, he could go through and then correct the problem, which turned out to be one side heater was not operating like the others or like the other equipments. Second example that I show is the contact resistance in the back of the line. So that would be a via between metal 1 or metal 2 or any of the metals. This actually occurred in the 65 nanometer mass production line. And you can see all vias 1, 2, and 3 in this case were the ones that were modeled. They all behaved by wafer. They all behaved in the same fashion. And we created a contact resistance model using these key indicators, and it was shown to have pretty good predictability, at least good enough for us to work on the issues. And here you can see that there were 4 key parameters that had to do with the barrier metal deposition, step durations, mean deposition, the DC voltage that was applied to the equipment, and so forth. And plus, it was both on the tantalum nitride and the tantalum deposition in the bimetal film. So this is very key, because now you can understand what the critical components to the via resistance. You can now take direct action. In this effort, this was done in an online mode. There was a learning cycle, which means basically taking the equipment parameters of all the equipments in this area. And then there was a prediction time after the model was built, and you can see that the prediction in violet was pretty well represented the actual measured distribution. So we think that some people might think that knowing information like this and how to control that also really goes to your reliability, because now that you know what key points in your contact structure, you can minimize variations in that contact resistivity that might be occurring out in the field. Finally, in terms of analog components, some analog components are, let's say, custom designed, like Taylor showed earlier today. Certain LDMOS structures that have various additional well implants and base implants and so forth. Other structures that are put into analog technology are built from the materials that are at hand, so to speak. In other words, in the back end of line, you build an inductor or a capacitor stack, and you utilize the dielectric depositions that are currently there. So if you can imagine that you had tighter variation on something that's not really tightly controlled, you might be able to have more precise capacitance values or inductance or even Q factors as a result. So in this case, we show that we can just do a basic dielectric model, and we're able to capture this on every single wafer. The point here is that in normal fabrication metrology, you only measure a few wafers out of the whole distribution, and you can't really see what's going on. In this case, there's some kind of chamber A versus chamber B issue that's causing a wider spread. And so, okay, yeah. And so, as I said, this is some strategies that can be applied to perfect or minimize the variation of these components that are built from the standard BUL structure. So finally, I'd like to summarize our talk today about analog yield strategy. We emphasized one core thread, which is minimize variation. I think the key thing is we would like to take advantage of advanced CMOS nodes that are going to become more available without an analog penalty, even when you're adding these components necessary to you to do your designs. Characterization, reduction, and control of variation is the key. And we can do that through the three steps or the three methods that I've outlined today. Deployment of the high volume characterization infrastructure to facilitate high precision modeling and PDKs with the tighter tolerances that will enable the smaller die areas for you. Use of the advanced fabric layout and circuit techniques that are now enabled by advanced CMOS nodes. That was the design techniques to, let's say, configure your, matched arrays to help minimize the offset voltage. And then finally, utilize, we call it yield-aware FDC fabrication line equipment modeling strategies to understand the sources of variation, and the process equipment and fabrication engineers can do their job to minimize those more effectively. Okay, thank you very much.